Hello, in this video I'll be working through Unit 4 homework problems 26 and 27. We're going to be using the first derivative test for Extrema and the second derivative test for Extrema. For the first problem, number 26, we're asked to use the first derivative test to determine the local extreme values of the function. That means we're looking for our relative max and relative min values. Our first function is y equals x squared minus x minus 1. So we start by finding the critical values. Critical values are the values of x where our derivative is equal to 0 or undefined. So we find the derivative. The derivative of x squared minus x minus 1 is 2x minus 1. Now we're going to set our derivative equal to 0 and solve. So we'll add 1, divide by 2, I get x equals 1/2. That's the only value for which the derivative is equal to 0. So that's my critical value. So I potentially have a relative min or a relative max at x equals 1/2. But to be sure, I need to check and make sure that my derivative changes sign from positive to negative or negative to positive. So I'm going to draw a number line. I'm going to place my critical value on my number line. At 1/2, my derivative, so y prime, my derivative is equal to 0. And this is the only place where my derivative is equal to 0. And that means for any other value, any other real number besides 1/2, the derivative is either going to be positive or it's going to be negative. It can't be 0 because the only zeros we found were x equals 1/2. So let's pick a test point. I'm going to use any value that is less than 1/2 as a test point. 0 is an easy one to substitute back in. So my test point is going to be x equals 0. And I'm going to look back at my derivative because I want to know if y prime is positive or negative. So looking back at my derivative equation, I'm going to substitute my test point in for x. My test point is 0. So 2 times 0 minus 1 is negative. That's a negative number. So I'm going to indicate that on my number line. Then I'm going to pick a test point to the right of 1/2, something that's larger than 1/2. I'm going to pick 100. So 2 times 100 minus 1, that's a positive value. So all x values greater than 1/2 are going to make the derivative positive. If the derivative is negative, then my original function y is decreasing. So I'll indicate that with an arrow. At 1/2, it's equal to 0. And then to the right of 1/2, the derivative is positive, which means my function is increasing. So I can see here visually that I have a relative minimum. And that's because my derivative is changing at this value from being negative to being positive. So we'll say our function f, in this case, our function wasn't presented in function notation, so we'll stick with y. Y has a relative minimum at x equals 1/2 since y prime changes from negative to positive. At that point. So that's how we justify the fact that we have a relative minimum. Part B, y equals negative 2x cubed plus 6x squared minus 3. Again, we want to find relative extrema. So I start by finding my critical values. And to do that, I need my first derivative. So y prime equals negative 6x squared plus 12x. I'm going to set that equal to 0 and solve. So I'm going to factor out a negative 6x, leaving behind x minus 2. Let me just double check that. Negative 6x times x is negative 6x squared, and then positive 12x. Okay, so we're setting that equal to 0. And since we have it in factored form, now we can set each factor equal to 0. We get x equals 0 or x equals 2. Those are my only critical values. There is nowhere where the derivative is undefined. So my critical values are at 0 and at 2. Those are the only values for which the derivative is equal to 0. So let's draw a number line. So we're doing our first derivative test. We'll put our critical values on our number line. And I'm interested in knowing what's happening to the first derivative, so y prime. At 0, the first derivative is 0. At 2, the first derivative is 0. And now we need to know what's happening at all the other numbers besides 0 and 2. So think about the interval between 0 and 2. I want to know if the values between 0 and 2 are positive or negative. Well, keep in mind that all the values between 0 and 2 have to either be negative or they all have to be positive. It's not possible for some of the numbers greater than 0 but less than 2 to be negative and then all of a sudden change to being positive, because the only way you can change from being negative to positive is to pass through 0 in between. And we know that the derivative is not equal to 0 anywhere in between 0 and 2. We've already found all the zeros. So I can pick, what that means for me is that I can pick any number between 0 and 2 to use as a test point, and then the sign of that one test point will be the sign for all the numbers in my interval. So let's just pick a test point of 1, and I'm going to substitute it back into my derivative right here. Now my derivative is also here equal to negative 6x times x minus 2. So which one should I use when I'm substituting in my test point? Well, we want to use the one that's factored. It's going to be easier to substitute into the factored form of the equation because I don't really care about the magnitude of the number. I don't care what the number is. I just care if it's positive or negative. So substituting in a 1, okay, so at x equals 1, we get negative 6 times 1 minus 2. So that's a negative number times a negative number. Negative times negative is positive. So those values are positive. Now let's pick a test point that is less than 0. I'm going to pick negative 100. I like to exaggerate it to make it easier to figure out if it's going to be negative or positive. So negative 6 times negative 100 times negative 100 minus 2. Okay, so that's a negative times a negative times a negative, which is going to be overall negative. Again, I don't need to compute the value. I just need to think about whether it's going to be positive or negative. And then I need another test point to the right of positive 2. So let's pick 100. At x equals 100, and again, I'm looking back in my derivative, I've got negative 6 times 100 times 100 minus 2. So that's a negative times a positive times a positive. And overall, that is going to equal a negative. So we have a sign change at 0 and we have a sign change at 2. What is that telling me about my original function? Well, wherever the first derivative is negative, my function y is decreasing. Where my derivative is positive, my function is increasing. And where my derivative is negative, here my function is decreasing. So if y is changing from decreasing to increasing, that's a relative minimum. And if it's changing from increasing to decreasing, that's a relative maximum. So we have one of each in this example. So my conclusion, we're going to say y has a relative minimum at x equals 0 since, I almost wrote f prime, I'm so used to f of x and f prime of x, since y prime changes from negative to positive. At that point. And then similarly, we can say y has a relative maximum at x equals 2, since my derivative, y prime, changes from positive to negative at that point. Part C, y equals 2x to the power 4 minus 4x squared plus 1. We want to find relative maxes, relative mins. So we start by finding our critical values. We take our derivative, y prime equals 8x cubed minus 8x, and then we're going to set that equal to 0. I'm going to factor out an 8x, leaving me x squared minus 1. So we're letting that equal 0. I'm going to continue factoring. So x squared minus 1 becomes x plus 1 times x minus 1. So now my critical values are at x equals 0, x equals negative 1, and x equals positive 1. I have 3 critical values, and there's nowhere the derivative is undefined. So I'm going to place my critical values on a number line. So we have negative 1, 0, and 1. And what's happening to y prime at those values? Well, y prime is equal to 0 at each of those values. And now we're going to pick some test points and see whether they make the derivative positive or negative. So my derivative equation is here. I'm going to use the one that is completely factored for my test points. So when x is negative 100, when x is negative 100, 8 times negative 100 is negative x plus 1, so negative 100 plus 1, that's negative. Negative 100 minus 1, that's also negative. So I have negative times negative times negative is negative. Then I'm going to pick a test point of negative 1/2. 8 times negative 1/2 is negative. Negative 1/2 plus 1 is positive. And then negative 1/2 minus 1 is negative. A negative times a positive times a negative is positive. Now I'll test 1/2. So 8 times 1/2, that's positive. 1/2 plus 1, that's positive. 1/2 minus 1, that's negative. So now I have positive times negative, that's negative. And finally, I'll pick positive 100 as a test point. 8 times 100 is positive. 100 plus 1, positive. 100 minus 1, positive. Positive times positive is positive. And now I can see that my original function y is decreasing until negative 1, then increasing until 0, decreasing until 1, and then increasing after 1. So I have a relative min when x is negative 1. I have a relative max when x is 0, and I have a relative min when x is positive 1. Okay, so f has a relative minimum at x equals 1 and x equals negative 1 since, I called it f again. It's a hard habit to break. Y has a relative minimum at x equals 1 and x equals negative 1 since y prime changes from negative to positive at these values. And then y has a relative maximum at x equals 0, since y prime changes from positive to negative. At this value. Part D, y equals x times e to the power 1 over x. So we'll start by finding critical values. Y prime equals, I have to use the product rule here, so derivative of x times e to the 1 over x plus x times the derivative of e to the 1 over x. I need chain rule for e to the 1 over x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of 1 over x is negative 1 over x squared. So let's simplify this. And I can, let's see, factor out e to the 1 over x. And that leaves me with 1. So I take the e to the x out here, I'm left with a 1. I take the e to the 1 over x out here, and that leaves me with x times negative 1 over x squared. So my x over the x squared just is 1 over x, and then it's negative, like so. So I'm going to let my derivative equal 0, and then set each factor equal to 0. So e to the 1 over x equals 0 has no solution. Think about the graph of e to the x. The graph of e to the x looks like so. It's always positive. E raised to any power whatsoever is going to give you a positive value. So there's no solution to this part of our equation. So then we set 1 minus 1 over x equal to 0. Well, here we can think of 1 as x over x. So we get x minus 1 over x equals 0. And a fraction will only equal 0 when its numerator is 0 and denominator is not. So we solve numerator equals 0, we get x equal 1. So I have critical value at x equals 1. Now in this example, we also have a value where our derivative is undefined. If we let x equal 0, we get undefined. We have e to the 1 over x, so right there x cannot equal 0. And then we also have this 1 over x right here. So x cannot equal 0. So critical values, x equals 1 and x equals 0. We have two critical values here. So I'm going to put my critical values on a number line. And then we're going to consider what's happening to the derivative at each of those critical values. When x is 1, our derivative is equal to 0. When x is 0, our derivative is undefined. So I'm putting an x to indicate that it's undefined there. I don't want to forget that. The original function y is also undefined when x equals 0. So if we do get a sign change here, we can't call that a relative max or a min because the function is not defined at 0. That's not part of our domain. But we'll see what happens when we try our test points. So I need to put my test points into my derivative equation. And that was this equation right here in factored form. This equation right here is my y prime equation. So I'm going to put my test points in there. I'm going to test a point between 0 and 1, so 1/2. E to the 1 over 1/2 is positive. E to any power is positive. So I'm really mostly just concerned with the 1 minus 1 over x. I'm substituting in 1/2, so I get 1 minus 1 over 1/2. That's the same as 1 minus 2, and that's negative. So positive times negative is negative. I'm going to substitute in negative 100. When I put negative 100 in for x, e to the 1 over negative 100 is positive. And then 1 minus 1 over negative 100. We get a double negative there, which makes it positive. So here we have positive. And then I'm going to pick another test point to the right of 1. Let's go with positive 100. E to the 1 over 100 is positive. 1 minus 1 over 100 is positive. 1 minus 1/100th is positive. So we have sign changes around 0 and 1. That tells me my original function y is increasing up until 0, and then decreasing between 0 and 1, and then increasing after 1. But we have to be careful about calling x equals 0 relative max, because the function is actually undefined when x is 0. So this is actually neither, even though we do get a sign change there. Now sometimes your derivative will be undefined at 0, but your original function is defined. That can happen when you have a corner or when you have a cusp. So we don't automatically rule out that value, but we have to consider, if we get a sign change, we have to go back and consider what do we get when we substitute that value into the original equation. In this particular instance, we cannot substitute 0 into the original equation. It's not part of our domain. But the 1, however, is part of our domain. So here we do have a relative minimum. So y has a relative minimum at x equals 1, since y prime changes from negative to positive. At that value. Part E, y equals x times the square root of 8 minus x squared. So we start by finding our critical values. Y prime equals, I need to use the product rule to take my derivative. So I start with derivative of x, which is 1, times the square root of 8 minus x squared, plus x times the derivative of the square root of 8 minus x squared. We need chain rule here. It's in the form of square root of stuff. The derivative of square root of stuff is 1 over 2 root stuff times the derivative of the stuff. The derivative of 8 minus x squared is negative 2x. So my derivative, square root 8 minus x squared, and then I can multiply this x and this negative 2x to get negative 2x squared in the numerator. Actually, this 2 is going to cancel with this 2. So over square root 8 minus x squared. So that's my derivative. And I want to set this equal to 0 and solve. So I'm going to simplify this. Here on the left, I'm going to multiply the square root of 8 minus x squared by the square root of 8 minus x squared over the square root of 8 minus x squared to get a common denominator. So I'm multiplying this by square root of 8 minus x squared over square root 8 minus x squared. And that's going to give me just 8 minus x squared minus x squared all over the square root of 8 minus x squared, like so. And then if I continue to simplify that, now I have 8 minus 2x squared over the square root of 8 minus x squared. Now I want to know, when does this equal 0? A fraction will equal 0 when its numerator is 0 and its denominator is not. So we're going to let 8 minus 2x squared equal 0, and then just make sure our solution doesn't also make the denominator 0. So here I have 8 equals 2x squared equals 4, x equals plus or minus 2. If x equals 2 and I substitute it back into the denominator, I get square root of 4. That's not 0. If x is negative 2, I also get the square root of 8 minus 4, which is not 0. So both of these are critical values. And then we should also consider what values are going to make our denominator undefined. So that would be where the denominator is 0. And that's going to happen whenever the square root 8 minus x squared is 0. If I square both sides, I get 8 minus x squared is 0. I get x squared is 8. So x equals plus or minus the square root of 8. The square root of 8 is the same as 2 root 2. If x is positive or negative 2 root 2, my derivative is undefined. So we need to consider those as critical values as well. So I have 4 critical values. I'm going to place them on a number line. Two root 2 is larger than 2. So putting these in order, we have negative 2 root 2. Then we have negative 2. We have positive 2. And then we have positive 2 root 2. And we want to know what is our derivative equal at each of these critical values. At negative 2 root 2, our derivative is undefined. At negative 2, our derivative is 0. At positive 2, our derivative is 0. And at 2 root 2, our derivative is undefined. So we have a lot of test points to check. We've got 1, 2, 3, 4, 5 sub-intervals here. The first test point I'm going to choose is negative 100. So I'm going to go back to my derivative equation, and I'm going to choose the one where I had simplified it the most. So right here, I'm going to substitute my test points into this equation to see whether my derivative is positive or negative. At negative 100, I have 8 minus 2 times negative 100 squared. That's going to be negative. So let me just do that out here. Negative. I'll make it pink so it's easy to see what I'm doing. So numerator is negative. And then the denominator, when x is negative 100, okay, we have 8 minus negative 100 squared. So 8 minus a really big number is a negative number, and the square root of a negative number is not a real number. So that's a problem. The negative 2 root 2, numbers to the left of that actually are not in our domain at all. And now that I think about it, our domain, if we go back to our original equation up here, the domain, 8 minus x squared, has to be greater than or equal to 0. So our domain doesn't even include numbers that are less than negative 2 root 2 or greater than positive 2 root 2. So I'm going to go back to my number line, and I'm going to erase the part of my number line that is not in my domain. I don't really have to consider values that are not in the domain of the original function. Okay, so I've adjusted that, and now I only have to test 3 test points. So I need a number between negative 2 and negative 2 root 2. Let's use negative 2.5. Okay, so at negative 2.5, 8 minus 2 times negative 2.5 squared. I'm going to actually calculate this one because it's not an easy one to do in your head. Negative 2.5 squared. That gives me negative 4.5. So I have a negative value divided by, and then in the denominator, I have the square root of 8 minus negative 2.5 squared. That's a positive value. So negative divided by positive is negative. Now I need a test point between negative 2 and positive 2. So I'm going to pick 0 as my test point. So at x equals 0, when I substitute that in for the x, I get 8 minus 0, which is positive numerator, over the square root of 8 minus 0, that's a positive denominator. Positive divided by positive is positive. And then I need a test point between 2 and 2 root 2. So let's use positive 2.5 at x equals positive 2.5. 8 minus 2 times positive 2.5 squared, that's negative. Over square root of 8 minus 2.5 squared, that is positive. So negative divided by a positive is negative. And let's make some room over here. So I used my test points to determine where my derivative was negative, where it was positive. And now I can conclude that the original function y is decreasing between negative 2 root 2 and negative 2, increasing between negative 2 and 2, and then decreasing between 2 and 2 root 2. So relative min here at x equals negative 2, relative max here at x equals positive 2. So y has a relative min at x equals negative 2 since y prime changes from negative to positive at that point. And then y has a relative max at x equals 2 since y prime changes from positive to negative at that point. F. Here we have a piecewise function. So we have y equals 3 minus x squared for x values less than 0, and y equals x squared plus 1 for x values greater than or equal to 0. To get our critical values, we need to find our derivative. The derivative of 3 minus x squared is negative 2x. And the derivative of x squared plus 1 is positive 2x. To find our critical value, we need to know where the derivative is equal to 0. So I want to set my derivative equal to 0, but 0 is, well, okay, I want to set my derivative equal to 0 and solve. So we have two different pieces. The top piece, I can say negative 2x equals 0, and I solve that, and I get x equals 0. That's possibly problematic because x equals 0 is right where the domain splits in my piecewise function. So in order for the derivative to exist at x equals 0, we have to check and make sure that this is differentiable at 0. So we have to look at the limit of the derivative as we approach 0 from the left side and the right side to make sure that this is differentiable. So let's erase that for the moment. And let's check to make sure our function is differentiable when x is 0. So I'm going to look at the limit as x approaches 0 from the left of f prime of x, or y prime in this case. So the limit of negative 2x as x approaches 0 from the left is 0. The limit as x approaches 0 from the right of my derivative, 2x, is also equal to 0. So since the left-hand limit equals the right-hand limit, I know my function is differentiable at x equals 0. So therefore, y is differentiable at x equals 0. That means the derivative exists at x equals 0, and we've already figured out at x equals 0, the derivative is equal to 0. Y prime of 0 is equal to 0. And that is the only place where the derivative is equal to 0, so that is my only critical value. I have a critical value at x equals 0. So I'm going to place my critical value on a number line, and then the value of y prime, my derivative at that critical value, is 0. So I need to now pick test points to see whether the other real numbers make the derivative positive or negative. So let's pick a test point of negative 100. And we're going to put that into our derivative equation here. At negative 100, I'm in the top piece. Negative 2 times negative 100 is positive. So my derivative is positive. Now I'm going to pick a test point of 100. That puts me into the bottom piece of my piecewise function. 2 times positive 100 is positive. So my derivative is positive to the left of 0 and positive to the right of 0. that tells me my original function is increasing to the left of 0 and still increasing to the right of 0. So we do not have a relative max or a relative min for this problem. Y has neither a relative max nor a relative min since f prime has no sign change. We could also say F, and there I called it F again. Let's go back and call it Y, just because the problem was given in the form of Y equals. So I'm going to stick with Y. So Y prime has no sign change, or we could have said Y is strictly increasing. Number 27. We're going to use the second derivative test for Extrema to find local maxes and mins for our functions. Part A, y equals 3x minus x cubed plus 5. So I need to start by finding my critical values. The derivative of 3x is 3. Derivative of minus x cubed is negative 3x squared. Derivative of 5 is 0. So if I set this equal to 0 and solve, I'm going to factor 3 out. 3 times 1 minus x squared, set that equal to 0. I can continue to factor 1 minus x times 1 plus x equals 0. I get critical values at x equals 1 and x equals negative 1. From here, I have a choice. I could use a first derivative test. I could draw a number line, place my critical values on the number line, pick test points, see if I get a sign change in my derivative. That's the first derivative test. But in this problem, we're specifically asked to use a second derivative test. So for the second derivative test, we first find our critical values, and then we substitute those critical values into our second derivative. So let's find our second derivative. And I missed my notation here. My first derivative, y prime, equals 3 minus 3x squared. So my second derivative is just the derivative of 3 minus 3x squared. And the derivative of 3 is 0. The derivative of negative 3x squared is negative 6x. So there's my second derivative. And now what I do is I substitute my critical values into my second derivative. So I need to find y double prime of 1, and I need to find y double prime of negative 1. I'm substituting critical values into the second derivative. Y double prime of 1 is negative 6. That is less than 0. Since the second derivative is negative, I know my graph is concave down at that point, and therefore I have a relative max. Y double prime of negative 1 equals 6. That's positive. A second derivative that's positive indicates that our original curve is concave up. So I know I have a relative minimum there. Okay, so y has a relative max at x equals 1. X equals 1 since y prime of 1 equals 0 and y double prime of 1 is less than 0. And that's all we have to do for justification. Y has a relative min at x equals negative 1 since y prime of negative 1 equals 0. We need that to be true. We need to know that the first derivative is 0. At a max or a min, our first derivative is either going to be 0 or undefined. So y prime of 1 equals 0, and y double prime of negative 1 is positive. Part B, y equals x to the 5th minus 80x plus 100. So we want to find our critical values. We start by taking the derivative. Y prime equals 5x to the 4th minus 80. I want to set that equal to 0 and solve. So I'm going to factor out a 5. And then that's x squared plus 4 times x squared minus 4. X squared minus 4 is x plus 2 times x minus 2. So there's my derivative. I'm going to set it equal to 0. Set each of these factors equal to 0. 5 doesn't equal 0. X squared plus 4 doesn't equal 0. X plus 2 equals 0 when x is negative 2. And then x minus 2 equals 0 when x is positive 2. So I have those two critical values. Now I want to substitute those critical values into my second derivative. So my second derivative, I need to take the derivative of my first derivative. So rather than looking at factored form where we'd have to do a massive product rule problem, I'm going to go back to this original form, the 5x to the fourth minus 80, and take the derivative from there. So 5x to the fourth, the derivative of that is 20x cubed. And then the derivative of minus 80 is just 0. So I'm going to find the second derivative at each of my critical values. Y double prime of negative 2 would be 20 times negative 8. That's negative 160. And I don't even really need to know that it's negative 160. I just need to know that it's negative. So if you don't feel like calculating it, but you know if it's positive or negative, that's fine to just write that. Y double prime of 2. So for example here, I know it's 20 times 2 cubed. Well, 2 cubed is positive times 20. That has to be positive. So it doesn't really matter what the value of the number is if I know that it's positive. And now I can make my conclusion. Since the second derivative is negative, the original graph is concave down. That has to be a maximum. And y double prime of 2 is positive. Since the second derivative is positive, the original curve is concave up at that point. So that has to be a relative min. So y has a relative max at x equals negative 2 since y prime of negative 2 equals 0 and y double prime of negative 2 is less than 0. So we need both of those things to justify how we know we have a relative max there. Y has a relative min at x equals 2 since y prime of 2 equals 0 and y double prime of 2 is greater than 0. Part C. Y equals x cubed plus 3x squared minus 2. We find our critical values, so y prime equals 3x squared plus 6x. I want to know where that's equal to 0. I'm going to factor out a 3x, leaving me x plus 2. So we're going to set that equal to 0 and solve. We get x equals 0 or x equals negative 2. Those are my critical values. So I could do a first derivative test from here, but the second derivative test is actually going to be faster. The second derivative is 6x plus 6. If I want to factor that, it's 6 times x plus 1. Factoring it makes it easier to substitute in values. So now I find y double prime of 0, and I'm going to find y double prime of negative 2. We evaluate the second derivative at each of our critical values. Y double prime of 0, that's 6 times 1 is 6, that's positive. Y double prime of negative 2, that's 6 times negative 1, that's negative. Okay, so second derivative positive, concave up, I know I have a relative min. Second derivative negative, that's concave down, I know I have a relative max. So y has a relative min at x equals 0 since y prime of 0 equals 0 and y double prime of 0 is positive. Y has a relative max at x equals negative 2, since y prime of negative 2 equals 0, and y double prime of negative 2 is negative. D. Y equals 3x to the power 5 minus 25x cubed plus 60x plus 20. We find our critical values by taking the first derivative, so 15x to the fourth minus 75x squared plus 60, and I want to set that equal to 0. Looks like I can factor out a 15, leaving x to the fourth minus 5x squared plus 4. And I'll continue to factor that. This is in quadratic form, so it's x squared something, x squared something. I need to multiply to get 4, add to get 5, so 4 and 1. And I need negative in the middle, but positive when I multiply. So let's quickly check that. It's x to the fourth minus x squared minus 4x squared plus 4. That works. This can be factored further. This is 15 times x plus 2 times x minus 2 times x plus 1 times x minus 1. I have 4 critical values here. So critical values at x equals plus or minus 2 and plus or minus 1. So we have to check all of those with our second derivative. The second derivative, 60x cubed minus 150x. And I can take out, let's see, 30x, leaving 2x squared, that's 60x cubed, minus 5, just 5. So there's my second derivative. I want to evaluate my second derivative at each of my critical values. So y double prime of negative 2, y double prime of 2, y double prime of negative 1, and y double prime of 1. Y double prime of negative 2. 30 times negative 2, that's negative. 2 times negative 2 squared, that's 8, minus 5 is positive. So negative times positive is negative. So I can just say less than 0. And I should be able to do that for the rest of these without actually having to calculate. So at positive 2, 30 times 2 is positive. 2 times 2 squared is 8 minus 5 is positive. Positive times positive is positive. At negative 1, 30 times negative 1, that's negative. Negative 1 squared times 2 minus 5, that's negative. So negative times negative is positive. At positive 1, 30 times 1 is positive. The 2 times 1 squared minus 5 is negative. Positive times negative is negative. So negative second derivative means concave down. So concave down here and here. We have relative maxes there. Positive second derivative means concave up. So we have mins. Oh, I did that wrong. Negative, negative. There we go. Negative, negative. And then positive, positive, like so. So here we have a relative max, here we have a relative min, and a relative max. And we can justify that by saying y prime of each of these values equals 0, and then where the second derivative is negative, we have a relative max. Where the second derivative is positive, we have a relative min. E, y equals x times e to the power x. So let's find our critical values by taking our first derivative. I'm going to use the product rule. So derivative of x is 1 times e to the x plus x times the derivative of e to the x. Now I can factor out e to the x, and I'm going to set this equal to 0 and solve. E to the x is never equal to 0, So we can ignore that factor. And then 1 plus x equals 0 when x equals -1. That's my only critical value. Second derivative. Second derivative. Derivative of e to the x is e to the x. The derivative of x e to the x, well, I know that because that's what my y prime was. So e to the x plus x e to the x, or 2e to the x plus x e to the x, or e to the x times 2 plus x. Now I want to evaluate my second derivative at my critical value. So e to the power -1, that's positive. E to anything is positive. 2 plus -1 is positive. Positive times positive is positive. So if my second derivative is positive, my graph is concave up, and I have a relative min. Okay, so y has a relative minimum that says minimum if you couldn't tell, at x equals -1, since y prime of -1 equals 0 and y double prime of -1 is positive. Last problem, f. Our function is y equals x e to the -x. So we get our critical value by taking the first derivative, product rule. Derivative of x is 1 times e to the -x, plus x times the derivative of e to the -x, which is e to the -x times -1. And I'll factor out e to the -x, leaving behind 1 minus x. We're going to set that equal to 0. E to the -x is never equal to 0. 1 minus x is equal to 0 when x equals 1. So critical value at x equals 1. We find our second derivative. So derivative of e to the -x is -e to the -x minus, now I need the derivative of x e to the -x, which is my first derivative. Okay, this is getting complicated. Let's distribute that negative. So we have -e to the -x minus e to the -x plus x e to the -x. These are like terms. So we have -2e to the -x plus x e to the -x. And I can factor out, let's factor out -e to the -x, leaving me with 2 minus x. Let me multiply that back out just to make sure I didn't make a mistake. So when I multiply by 2, I get -2e to the -x. When I multiply by -x, I get positive x e to the -x. Okay, that looks good. Now we need y double prime of 1. That's my critical value. So when x is 1, I have -e to the -1 times 2 minus 1. So that's negative times positive is negative. Negative means the original curve is concave down at that point, so I have a relative max. Y has a relative maximum at x equals 1, since y prime of 1 equals 0 and y double prime of 1 is less than 0.